Next up, we have Dr. Kevin Quinlan from Lawrence Livermore National Laboratory. Dr. Quinlan is a member of the Applied Statistics Group at Lawrence Livermore, and he has a PhD in statistics from Penn State, and he focuses on design of experiments, Gaussian process modeling, and active learning.
So I just want to start off thanking all my collaborators on this work. Sheeny, Annie, Siva, and Paul all helped a lot with this, especially Sheeny. She was my summer student and did a lot of the work that you'll see today. So the example that we're looking at is going to be involving trajectory simulation. So what you can see here is probably pretty familiar for a lot of people in this audience, but just going to walk through sort of how this would work is at each time step, right, you're going to run through a trajectory simulation. You're going to check a lot of different things, but one of those that we're going to focus on is an aerodynamic database. And so these have a lot of different parameters that are going to influence the flight of the vehicle in your simulation. So for example, at each time point, you might calculate the speed that it's flying, the angle it's pointed, a lot of these different things, and then you're going to check it against this database because running the computational fluid dynamics at each time point is just, basically impossible to do that. So one thing that you might think to do is just try to do like a full factorial, which would be like a grid of high fidelity CFD, but that, as you start to get more parameters, is going to be really just computationally impossible to fill out. And as you start to get even like higher parameter, larger parameter spaces, it's even for lower fidelity, it's just kind of like very wasteful to do this. And so to facilitate like this whole process, we're going to be using surrogate models, specifically GPs and deep GPs, and using active learning to fill the database out efficiently as possible. So in the past, like we've done work where we use trajectory information, interim trajectory information to inform where to sample, and multi-fidelity methods. But today, what I'm going to focus on is what's called a trimmed error database. So this is going to be like the example vehicle that we're going to reference here. This is called the High-Speed Army Reference Vehicle, or the HARV. And we're going to look at mach, alpha, and side slip. So those are just the angles of the vehicle. And it has 4 controllable fins, as you can see in this nice little GIF over here. And so the idea is that we can actually reduce the space that we're exploring by finding 3 of the outputs from the CFD simulation are called the moments. And if we can find where these are all 0, that's essentially saying where there's stable flight, as I understand it. And so the goal is we just want to build up this database in a case where those outputs are 0 for any of the input conditions. And so this is still in progress. So this is going to be a simplified version that we're going to look at, where we are looking for this trim condition where the result is only going to be like a single trimmable point. But in general, that's not always the case. So that's future work. So just looking at an example here for the HARV geometry. So this is fixing the top and bottom fin. We're only moving the left and right fin. You can see 2 of the responses here where we would want to find the 0 condition, the roll moment and the pitching moment. And so you can see here the black lines are, maybe I should have made 1 on each, but showing where those contours are actually 0. And so in essence, what we're trying to do for this fixed condition is find where this crossover point here, this is the trim condition where both are 0. And the results here come from like a larger, somewhat sparsely sampled, a larger database. We fit a surrogate model to get these responses. So that's why it's maybe a little curvy here instead of something maybe that you'd expect exactly from the CFD. Okay, so this is the example we're going to be trying to do. We're trying to find this trim condition. So after the last talk, I probably don't have to give a huge introduction into GPs, but in case anyone just joined and is not familiar with GPs, it's a function where it's defined by its mean and covariance. If you take any collection of these points, it's multivariate normally distributed. And we really like Gaussian process models, not only for their ability to fit these structures well, but also for their uncertainty quantification. So you can see here, this example over here, you could imagine if this was your error database, you would have actually different sample draws that you could propagate forward into your simulation to try and account for that uncertainty when you generate trajectories. So so the Gaussian process model, we're going to just assume sort of a constant mean that's estimated from the data. And the covariance structure that we're using here, or kernel we're using here, is going to be the Matern kernel. So the Gaussian process model is the first model we look at. The other one is a deep Gaussian process. And so I won't be using this for the example today, but I will show another example that uses these. So deep Gaussian process model is nice because it can handle non-stationary features. And the way this works is it actually warps some of the inputs using latent Gaussian process models. And this is really nice because we do it in a fully Bayesian way, so you actually get the uncertainty quantification that you would expect from a Gaussian process model. And this is done using the R package deepgp for the implementation. And you can see here sort of an example where you're taking like a regular GP and warping it to a 2-layer GP. You could do multiple, but typically we use 2 or 3 layers. For this talk, it'll just be 2. And you can see as an example where this could be useful. So if you had some feature where it's a non-stationary feature, like in the step function is kind of an extreme example. The traditional GP, you get very large uncertainty on those 2 tails, even though it's a relatively flat feature here because it's stationary, so it's assuming sort of the same, for lack of a better term, wiggliness, right, based on that step function in the middle. But using the deep GP, we can actually adequately capture this well and get something that looks more reasonable for the uncertainty on either end. So those are the 2 models we'll be considering here today. But in addition to just building the surrogate model, we want to have some acquisition function that allows us to capture that trim condition. So to start with, we started thinking about so what are some of the possibilities, methods that are out there? So the first thing we started thinking about was active learning for contour estimation. And so the idea here is that we want to find this target region. So here you can see on the plot on the right, I'm showing what's called the entropy criteria, where we're looking at for a small set of data, small samples of data, what would be that estimated target? Where would be a good place to acquire new data for the target, which was where that value is 0. And so there's a lot of different methods out in the literature. So just thinking of, there's a few that I've listed here. One tries to minimize prediction variance around this contour. We also have the entropy that I've plotted out there. And so that is a nice way in terms of really exploiting where you're trying to find the target region. But it's not very good at the exploration side of things. So to balance that out, this paper actually uses a optimization scheme to try and to encourage exploration. But yeah, so there's a couple of different methods. These are all trying to target the contour. However, if you just apply these directly, it doesn't really give you what you want, right? Because the overall goal is actually we want to find where all of these contours intersect. So we want to find the X point where all of the responses are 0. This could generally be a different target value, but for ours, it actually is 0. So that's why I have it listed there. And so, if you apply existing methods, you can discover the contours pretty well. You could try something where you alternate between the different contours. However, you're actually wasting a lot of your samples in regions that aren't even close to where the 2 cross over. And so we wanted to come up with a criteria where we would be able to target that area. And so, yeah, we're focusing on the case where it's a single crossover point, but like I said, we're looking into where these actually have like a whole region where they're overlapping. And so to start, we want to propose something that's more aggressively exploiting samples near that target. Okay, and so the approach we're proposing right now is to use this kind of joint probability criteria. And so the idea is we want to find the area where for some tolerance delta, that the difference between the target value and our Gaussian process predicted mean y is within, or well, where the value is actually for the function y is within some delta. And so you can see here comparing, right, if you just look at entropy where you are sampling along the whole contour, using something like this actually does target the crossover region. So even with some limited data, we already have a pretty good idea of where this point is going to occur. And so here we're treating the probabilities as independent, so we can take the probability just by, multiplying all of those. And so rather than fixing delta initially, we adaptively shrink this over the acquisitions so that we can narrow in on the trim condition value. And so right now, the way that we've been working on it, and we're still sort of developing, because I think this could be improved a little bit, is that we're using the current best value of the simulation of how close it's getting to the target value to adapt the tolerance value. And so the optimization is really fast when using the GP because you can get lots of predictions, you can search over a dense grid. But for the deep GP, it's going to require a little bit more work. And so that's something that we're still looking at. And so I just wanted to walk through an example here where we have an example where we're going to use a deep Gaussian process model and just walk through how this works. So this is the Gramscian-Lie function on the left, and then on the right, we essentially warped that a little bit and rescaled it so that it's stretched. And you have this crossover point here in the lower left. It's denoted by that red triangle. And so if we collect some initial random Latin hypercube sample, you can see the predictions are getting like a decent representation of that contour initially. It's not dead on or anything, you know, the one on the left kind of looks like an avocado popping up. But we get these predictions with the mean, and then you can see the uncertainty. One of the nice features with the deep GP is that these areas on the right, so if I go back, if you look at the surface, most of the features are occurring either in the bottom left or on the left side for surface 2. With the deep GP, it's nice because we get something where the uncertainty is really low in those outer regions. It's doing a good job of finding where those values are relatively flat. And so now if we take these and we look at the criteria, so if we look just at the y within tolerance for the left plot and the middle plot, you can see that it is sampling around essentially like that shape we were seeing for the mean. And if we look at that joint region, zoomed in here, it's really focusing on close to the contour. And that overlap point is, you know, maybe not the most likely value to sample, but it's within that band. So the star is where we'd add the sample. We can continue on. And then, yeah, you can see you're much more likely to sample close to the point. Looking at the tolerance region, it's shrunk just because now we're closer to the target value. So, okay. We want to apply this in a simulation study now for the hard geometry. And so rather than actually run CFD, because we're going to be running this multiple times, the way we set this up is I used a surrogate model on a larger data set, fixed a couple of conditions. And so you can see here the plot I showed earlier. This is the surface that we're going to be looking at. And so even though I'm just looking at one fixed mock alpha combination, we can get similar results for the different values because we see sort of like similar type of behavior. Like it's not like extremely different from a surrogate modeling perspective. Okay, and so for the first case, we are fixing the top and bottom fin. We're only looking at the left and right. And so we only have two responses here, pitch and roll. If we look at the second case, then we are only fixing the bottom fin. Just to keep this a little simpler, so we have three responses then, pitch, roll, and yaw, and we have three inputs. So it's a slightly larger parameter space we're exploring. As far as the acquisition functions we wanted to compare it to, we use our joint probability criteria we're proposing. We're also looking at alternating the entropy. So this would be just trying to find the contour values for each of the individual responses and a max-min Latin hypercube design as sort of like a control using a space filling design. Yeah, we tried a couple of other methods. I didn't list them here, working with that entropy, but I thought this was probably a good one for comparison. And yeah, so we're essentially just looking at the RMSE based on the true trim location. So that crossover point right there, we're seeing how close our best predicted value gets to that in terms of the input dimension. And I used 1 to the -5th as an arbitrary stopping point. So you can see here, just running through this, we started with 4 samples that, using this joint probability criteria, we're able to get to the trim condition really quickly. It only took maybe like 10 at most, like 12 samples using this simulation study. So maybe a little surprisingly, the entropy approach doesn't do that much better than using a space filling design. And I'll show why on the next slide. But both of these, eventually they'll get there, but by targeting the actual criteria you're trying to get to, you get there a lot faster. And just showing 2 example designs here that might give some intuition why the entropy wasn't performing that much better than space filling, because if you think about those contours, they cover a lot of the space, and these samples look very good in terms of like where they're trying to give you a better estimate of those contours, but it's not targeting that exact value like what we would like. And so that was like a full 30 samples. If you look at the joint probability design here, we started with 4 with a random Latin hypercube. You can kind of see that it's like zeroing in on the target point. Okay. So then going to our second case, you can see this is using the 3D case starting with 8 samples. Some of them, it actually got it within adding 1 or 2 samples. Likely for those cases, we had something from the initial space filling design that was relatively close. And so we were able to get something really quickly, maybe a little bit of a larger tail out there in terms of the performance. But I think partially this is just because the way we're doing that tolerance reduction is maybe a little conservative. And so you could probably have something that is more aggressive to get better performance, but it's something we're still looking at in terms of fine tuning this algorithm. Okay, and so for the last simulation study I wanted to look at, I wanted to use one with the deep Gaussian process models. So this is the example I was walking through earlier with the Gramsci and Lee functions. We're using the deep GPR package to fit this, and you can see here one is the original Gramsci and Lee, but shifted a little bit so that contour at 0 had a slightly different crossover, and the other one is scaled a little bit so that it's like rotated and has maybe a slightly different shape to it. And so we're looking at the same methods here, and interestingly, this one, it takes definitely a little bit longer for things to converge. You can see the initial samples, though, that it does start to buy down the error a little bit more quickly in terms of finding it. And then once it gets close, it really, eventually, it samples almost exactly on the crossover point. Versus the space filling design and the entropy, it's not converging as quickly. And so this was actually a really interesting case when we were looking at things before. Is so the entropy criteria um, for this case, because there's like a very small region. So if you look at the one on the bottom or the surface one, because there's only like a small region where you have values that are above the contour line. If you don't get anything sampled inside of there initially, it can take a while for it to actually identify where that contour region is, and it'll sort of meander a little bit. And so I think that's part of why it's performing a little bit worse here comparatively to the space filling design. Um, so, okay. So in conclusion, this joint probability criteria is very effective at finding the trim condition. And so the traditional contour estimation methods didn't work as well. Just in essence, they weren't built for the specific application, and you're wasting a lot of samples, kind of exploring regions that aren't very helpful for your target goal. So one of the things that I think is going to be interesting is extending this to the case where we're modifying this so that we're looking at more than just a single point, right? Then the crossover of these contours are going to be contours themselves. And so I think, yeah, it's, in addition to that, it's also a larger space that you're exploring. So rather than just 2 or 3 parameters, we're going to be looking over 4 fins and additionally over the full range of the Mach alpha parameters. Yeah, and so additionally, we need to do some further refinement of the optimization scheme. And one of the things that I think was really helpful just for building regular error databases was, incorporating trajectory information. There's cases in that space that like you're never going to fly, and so you don't need to waste samples buying down error there. And so I think all of these things that we did for regular error databases can be applied for this as well. And so I think that'll be an interesting space to explore. So those are my slides, and this is my contact if you want to email me. So thanks, everyone.
Questions? So you're trying to find where 2 functions are 0, right, at the same time. So I guess naively, I would have just squared them and added them together and got like a minimization.
Yeah.
You have thoughts about what the pros and cons of an approach like that would be?
Yeah, so we tried a lot of different things initially. I think one of the problems you run into there is like you could get a function that's way more complicated, right? And versus maybe some simpler functions that you're fitting independently, if that makes sense. Yeah, in terms of just using that for the criteria, I don't think that performed as well when we were testing it out.
Okay.
Yeah, we tried other things like just summing the entropy, right? And sometimes, when you're going through this, you get some unintuitive results that maybe you're like, oh, this should work really well. And then like the entropy, right? If one of them isn't working well, you're essentially just targeting one of the contours.
So you've come up with this active learning idea here to fit a model to find the 0 point in function of those factors of the aerodynamic problem. Could this be applied in like a wind tunnel testing situation too? Like I know you use the truth data as your GP that you got from the simulation database, but could you say they were doing some wind tunnel testing? Could you apply this to try to experimentally find where the trim conditions are? Is that feasible?
Yeah.
Is that not useful?
Yeah, I guess like the way I'd be thinking about that is, you could definitely apply the wind tunnel testing data here. I would think the way you'd want to try and do this is maybe build it up as like a multi-fidelity model. And so you could use whatever you've done from your mod sim to give you a better initial idea of where to sample or to run your wind tunnel tests. I know, there's some different constraints with testing for the wind tunnel, but certainly we could use that to help inform where you'd want to run the tests.
So with the deep GP is interesting. I've never seen that before. Was it is there a customization like with your normal GPs you can do lots of customization? How easy was it to use and was it customizable?
Yeah, so the deep GP is pretty easy to use. Yeah, it's a fully Bayesian method, so you have to worry about like some of the Monte Carlo steps, but it's really pretty straightforward to run it using the R package. Andy actually set it up. It's really, yeah, really convenient. Um, yeah, and in terms of just like it's pretty flexible in terms of the features it can fit. So we had an example that we used for this that it goes over like a transonic regime, right? And so there you're going to get something that is definitely very non-stationary in the fit. And so, yeah, in terms of flexibility, yeah, you can choose all of the different kernel types, like what you're using for a regular GP. So, yeah, highly encourage you to try it out.
Thank you.